Your Zoom.
Okay. Hi, everybody. Welcome to GAAC.
Yay!
Hi, we're honored to have in person Dr. Harry Ferguson,
Ferguson.
who's from the Space Telescope Science Institute. Sorry, too much to remember. And he's done a lot of interesting work over the years, including working on the Deep Field project with Hubble, and he's currently working on a survey of distant galaxies using the Hubble, and he's also the deputy project scientist on the James Webb. So he's done lots of things for NASA. So please welcome Harry.
And can I just test, can you hear me online?
Arthur, can you hear him?
Yes.
Yes, indeed.
All right, thank you, Alan.
Great. Well, it's a real pleasure to be here. And I want to just say, feel free to interrupt me. The stuff I have laid out here, I can skip through, so on and so forth. So, we can make it interactive if you want to stop and ask questions. I decided to do sort of a jaunt through where we've taken a bunch of telescopes over the years and pointed really at sort of boring, typical places on the sky, like to be representative. So it's like taking these very expensive telescopes and pointing them at nothing and see what we'll see. So that's more or less what I'm going to talk about. But I want to give you a little bit of my history. So I started out as an amateur astronomer in the astronomy club at my high school, St. Paul's School in New Hampshire. And so that telescope there in the little dome on the left-hand side is the first telescope I used. And I was actually privileged to have pretty good telescope. It was an Alvin Clark 5-inch refractor that had been there since the early 1900s. Then the science teacher at the school had found that there was a sort of an unused telescope that was 10-inch on Fisher's Island, which I happened to be where I spent my summers. And so I had that to myself for a few summers. And that telescope not only had 10 inches of refraction, but a massive Warner Swayze mount. So this thing was very stable, clock drive, everything. Had a double slide plate holder for taking pictures and a spectrograph. And so, high school junior and senior, and I'm trying out spectroscopy, and I'm trying out taking long exposures, and that was just absolutely cool. Then when I went to college, I went to Harvard, and they had just launched the Einstein X-ray Observatory when I was looking around for a research assistantship. And so in junior, senior year, I ended up doing X-ray astronomy, and that was sort of in the early days of X-ray astronomy. So they had taken that telescope and pointed it at just stars to see what do stars look like in the whole X-ray spectrum. And so my first summer project was, let's just take all the stars and figure out what they look like in the X-rays. And so it was a very cool project. My advisor, who I'll have a picture of on the next page, went off on vacation for a few weeks. So I'm sitting at my advisor's desk with all these X-ray spectra of stars out in front of me, and I felt like I was in heaven for the moment. Then I went to Hopkins for grad school, and I went to Hopkins partly because the Science Center for Hubble had just been selected to be at Hopkins, and Hubble was going to launch in a few years, and that was in 1982. And it became apparent that Hubble was not going to launch in a few years. But I also started on a project that was very cool, which was a telescope called the Hopkins Ultraviolet Telescope, which was going to go up in the space shuttle in just a few years. And as opposed to Hubble, as a student, I could help build the thing. So I didn't actually do any of the optics, but I tested the optics of the spectrograph in vacuum. I wrote a whole bunch of software for it, and there's a lot of hands-on stuff that you could do. And that was supposed to go up in 1986 for the passage of Halley's Comet in the shuttle right after Challenger exploded. And of course, that got delayed. So, but it did go up. I was already a postdoc up in Cambridge, England, when it went up. So I was flying back to the US for many, many launch attempts. It finally went up in December of 1990, observed from the aft flight deck of the space shuttle for 10 days or so, and then went up again in 1992. Hugely successful in the end, and really sort of got me started on being interested in both hardware and software and all sort of aspects of doing astronomy. So I just wanted to show a few of my mentors along the way. So Walter Hawley was the science teacher at St. Paul's School who got me into the whole thing, and he was one of these teachers who was just thrilled with discovery and wanted to sort of co-discover along with the students. So when we did crazy things with the telescope, he was encouraging them. Rick Harnden sort of got me to think like a scientist. He was my advisor when I was an undergrad. Art Davidson was my first advisor at Hopkins and was the principal investigator on that telescope, the Hopkins ultraviolet telescope. Then when that was clearly delayed, I was looking around for a new thesis project, and Alan Sandage was spending some time at Hopkins and had some data he had already taken, which was perfect for a student who didn't want to spend another 10 years in graduate school. And so I ended up working with him on a project where he had already taken these giant glass plates. They're actually this big from the DuPont telescope.
Plates from?
What's that?
What scope would?
They were from the DuPont telescope in Las Campanas in Chile. So wide field of view. I was looking at them by eye and finding individual think galaxies and essentially cataloging and trying to understand the properties of those galaxies. He was a really delightful person to work with if you were on his good side, which I pretty much always was. He was notorious if you got on his bad side. But he also, I always thought, was sort of tongue-in-cheek even when he was being notorious. So Hubble Space Telescope launched in 1990. It launched with a serious flaw in the primary mirror. It was actually ground to the wrong figure. They had various signs that had happened that they ignored, but nonetheless figured out how to give it corrective optics, and shuttle flight in 1993 put those corrective optics in, and they essentially repaired it to pretty close to the original specifications.
How did they correct it?
So I don't know the details of the optical prescription, but the mirror itself was classical spherical aberration, and they just put in some optics in the intervening path to correct the spherical aberration. So they didn't do anything to the mirror itself. They just put in some lenses. Yeah, they gave it glasses. Yeah. And they had to, so they had one, it had a camera that sort of occupied more of a central region in the focal plane, and then spectrograph and other camera and so on. And they had to do different things. They put in a new camera, gave it its own corrective optics, and then they put in a thing called CoStar, which put little fingers with mirrors on them to give you the correction for the other instruments.
The package looked like a phone booth. It may be the last working phone booth.
If you look at this picture here, you'll notice the solar arrays are different from, whoops, I gotta go back. This picture here. So they actually, those solar arrays, those first solar arrays also snapped every time you went from night to day when it was orbiting. So they eventually replaced those with ones that didn't have that thermal problem. So anyways, telescope went up. I had gone off for a postdoc in England in 1990. I came back in September of 93. Telescope was repaired and good to go, and I was already thrilled to be working on a few projects. And I got very interested in galaxies and galaxy evolution. And I just want to sort of give you a fuzzy idea of some of the key questions that were floating around at the time. One of them was that there was supposed to be an epoch of galaxy formation. There was the thought was, we see these big galaxies, especially elliptical galaxies today, know they're old. They had to have formed their stars early. There's various chemical arguments for why they had to have formed their stars rapidly. So the epoch of galaxy formation would have been when they were forming lots of stars really fast. They should have been big, bright explosions. And so one of the the holy grails was, let's go find the epoch of galaxy formation. People were searching for the epoch of galaxy formation. Another thing was, even from the ground, we were counting galaxies and measuring their brightnesses, and the deepest images taken from the ground had lots and lots of faint blue galaxies in it. And when you try to take today's number of galaxies and project back in time and put them in wallpaper, you didn't get nearly as many if you used the cosmological and galaxy evolution models that were available. So there was a severe faint blue galaxy problem. Basically, there were too many. We didn't know quite where they were in distance, but there were too many of them. And there were all sorts of ideas floating around for how to fix that. And that's what I sort of spent some of my time at Cambridge on, was trying to come up with crazy ways to fix that problem from the theory side. None of them were right. And then the other question was, at the time, the favored cosmological model was the universe itself is at critical density, so on the cusp of expanding forever, never collapsing, but right on that cusp. And it is closed by mostly the gravitational attraction of dark matter. And so dark matter is the dominant constituent of the universe. And that model explained lots about galaxies, lots of observations that we had. But that model predicted far fewer of these faint blue galaxies. So one of the tensions was that model really was not predicting as many galaxies. So 1993, Bob Williams, I guess we're at around 94, we're looking at lots of images from the refurbished telescope. And he was director at the time. He was not an astronomer interested in galaxies, but he had discretionary time and was asking around, and he would ask at science copy at the Institute, he'd ask the postdocs, and I was a postdoc at the time, what should I do with my 300 orbits of discretionary time? And many of the postdocs were people who studied galaxies, and he got interested in galaxies, but more as a cheerleader than that was his specialty. And he said, yes, I would like to take half my discretionary time and put it towards studying galaxies. And so he decided, first of all, to ask the colleagues at the Institute what we would do. And so we would talk about this at coffee over a week or two, and sort of started by saying, well, what if you just took all of that time and put it on observing one spot of the sky for as deep as you could possibly go with this telescope? And that was the craziest thing we could think of. But then we started to think about, well, what would it look like? And realized, well, A, we don't really know what it looks like, but B, it would look pretty cool. And then, so we sort of worked that out, and I took some of those crazy models I was working on, and I did actual predictions of what it would look like for different models. He brought in an advisory committee. The advisory committee debated a whole bunch of different things, mostly people's own favorite things to point at. And the least common denominator turned out to be, let's take it, pick a blank spot in the sky and point at it for the whole amount of time. And so the only evolution of that was, instead of doing one filter, let's use 4 filters. And there was a clever way to make the time much more efficient by making one of those filters in the ultraviolet and observing during the daytime in that filter. And so we did that, and it was about 2 weeks of time, 350 exposures, and then we co-added them all together, and that became the deepest image of the sky.
How many exposures?
Yeah.
Curious.
About 350 exposures, yeah.
350?
Yeah. And we had to come up with a way, so you want to make sure the thing you're seeing is not a flaw in the detector. So you move the telescope, and then you have to put the images back together. And we had to come up with a way that we thought was sort of doing the most faithful reconstruction, given that there's geometric distortions in all the lenses and so on and so forth. So there was a fair amount of software development to just try to get this to work. But so we chose that spot. One of the key things was, if we were going to use the 4 filters, it turns out Hubble most of the time is blocked by the Earth because it's in low Earth orbit and it's going around. And so it's only 50% efficient most of the time, or less than that. And but there are two spots, north and south, roughly in the ecliptic pole, where you can observe all the time. So we said, let's pick a spot in one of these continuous viewing zones. And we chose the northern one, which is further out of the plane of our galaxy. And let's just go find a spot that has no bright stars, no dust clouds, nothing of interest. And so we looked through to find something that was boring, but in the continuous viewing zone. And then the other problem with the continuous viewing zone is because you're observing, the Earth is here, you're observing like this, you get scattered light on the bright side, and the optical filters are affected by the scattered light, but the Earth's scattered light is not much in the UV. So we could observe the UV when we were on the bright side, and then the optical. And that's how we got a factor of 2 roughly improvement in efficiency. And we got the ultraviolet, which was pretty crucial for some of the things we wanted to do.
That's great. The Southern astronomers have enough eye candy.
A few years later, we came back and did a Southern deep field, but it was, when you do the second one, it's never got the impact of the first one. So then what you got from that image is you've got colors. So that gives you some information. I'll show you a little bit about how we use that. But you really want to know where the galaxies are. So you need to go measure redshifts, and I will give you a little review of that in a second. But you need a big telescope to do that, and Hubble just doesn't have the sensitivity. So this was done from the ground. Keck Observatory did most of the early redshifts. At the time before this observation, the redshift record for a normal galaxy, not a quasar or a radio galaxy, was about a redshift of 1. And there was this sort of barrier where people knew there had to be galaxies at higher redshift. There was lots of evidence that galaxies formed earlier, and somehow we weren't finding them. And right about the same time as we took these images, there was a breakthrough just in figuring out what the spectral feature was to look for, and in sensitivity and where to look. And so there were tens of galaxies in the image here that were identified at redshift about 3, about the same time as ground-based surveys of other spots in the sky also found galaxies at a redshift about 3. So it wasn't the Hubble Deep Field that broke that redshift barrier, but it was using techniques that sort of interacted between the two, groups of people working on the same sort of thing, came up with the same ideas and so on. So that's looking back to about 2 billion years from the Big Bang. So the light left those galaxies has taken 11, 12 billion years to get to us, and then that we're just seeing it now. So they were very young when the light left. That part of the sky you're seeing is about the size of a grain of sand held at arm's length. And the brightness of the faintest dots that you could see is about a photon per week, striking. And there's about 1,500 galaxies that were cataloged in that.
So what's the magnitude of the faintest star?
Faintest ones here were, I'm thinking about 28 in sort of an optical band. So just to, probably everybody know in this astronomy club knows about spectra, but spectra are key for getting more information than we can get from the images. So you have a spectral energy distribution, which can tell you something about, even if you don't have any spectral features, you can get something about the temperature of the thing you're looking at. You can get some information about whether there's dust and something intervening. And then if you have spectral features, you get chemistry, you get much more information about temperatures, so on and so forth. And you get a redshift, because those spectral features that you see in the lab will be at a different wavelength than from a galaxy that is receding from us in the universe, or expanding with the flow of the universe. So as you go further and further out, there is very, very not dense diffuse gas in the intergalactic medium. It's mostly hydrogen sitting in the intergalactic medium between us and these distant galaxies. but there's enough of it that you actually, it starts to eat away the spectrum. And, going, and so as you essentially move further and further through that line of sight, you'll hit an individual cloud that'll eat away an absorption line. And that gives you lots of information about the intervening gas. But as it eats more and more away, it gives you a feature that you've got light here, and then you've got a break there. And that's a characteristic feature that we use all the time now to find distant galaxies. And so when you look at a lower resolution spectrum, now that was a quasar, this is a galaxy, you'll see this break. It's at the rest frame, depending on your redshift. Usually it's for high redshift galaxies, most of the light is eaten away at a rest frame of 1200 angstroms, which then can be shifted out way even into the infrared if you're looking at super high redshifts. So that, now if you have a spectrum, you can see the break, but if you have even just the 4 images of the Hubble Deep Field, you can see the galaxy there in the red band, there in a green band, there in a blue band, not there in the ultraviolet. And that was what gave us the candidates of the galaxies at a redshift of 3 that we could follow up with spectroscopy to actually pin down where they are. So that's called Lyman break selection and became the tool that we use. So we started counting galaxies at these redshifts. And one of the first things to do was just say, well, okay, how many do we see? So we'll start writing a paper about how many we see. And Pierre Madao, who was a postdoc at Space Telescope, said, well, why don't we divide by the area, the volume we're looking at, and let's look at it density. And then we can convert the brightness of the galaxy. Pretty much all that light is coming from star formations, from young stars. So we can estimate with pretty good accuracy the star formation rate. So we've got a star formation rate density of the universe. So let's plot star formation rate density of the universe, number of stars formed per cubic megaparsec per year, and plot that as a function of redshift, and see what it does. These are ground-based estimates, and this is what we were getting from the Hubble Deep Field. And you know, formally there were lower limits, so we really didn't know whether this thing kept going up or not. But we put it in the paper, and this, first of all, the paper was rejected by the first journal. Submitted it to another journal, they accepted it right away, so who knows. We didn't make much of that plot. But then Piero in later talks actually drew a curve on that plot, which he had no basis on which to draw it, but he drew a curve on that plot. And that became known as the Madao diagram. And this is like one of the most cited papers in astronomy, with a plot that we thought, yeah, okay, it's suggestive. And it is a very cool plot because it not only tells you star formation, but those stars are forming all the chemical elements, anything heavier that wasn't formed in the Big Bang. So you can infer when all the chemical elements were, if you could actually do this problem accurately, which we really couldn't do at the time, but we were at least trying to do what we could with the Hubble Deep Field. So I'll get back to that one because I want to show you different versions of that plot. It's gotten a lot better. The other thing that happened right about a few years after the Hubble Deep Field was taken was research groups who were looking at distant supernovae, which are pretty good standard candles. They go up with a brightness that's almost the same, and you can calibrate based on their colors and their light curve shape. You can calibrate to a pretty good accuracy. It was clear that they were fainter than the favored model of the expansion of the universe would expect. And they, if you didn't ascribe that to not understanding supernovae, and instead not understanding the universe, you needed a universe that was accelerating. So it was originally expanding and decelerating, and then started speeding up again. And that you could put a constant into Einstein's equation. It's called lambda, and it's called the cosmological constant. And you put that in, and you can say, well, there is this dark energy that essentially exerts a pressure that causes the expansion of the universe to speed up. And so dark energy was discovered by the supernova measurement. It represents about 70% of the mass energy density of the universe. We don't know what it is. And that was back in 1998. As of 2 years ago, there are thousands of supernovae. They track this. And this is not the only kind of measurement that is telling us the universe expansion is accelerating. We're very confident the universe expansion is accelerating from multiple directions. So that's happening. The other thing that's happening is, okay, that model, this with the cosmological constant, is looks like it fits almost everything, and there are now chinks in that preferred model where it's not fitting everything. We don't quite know what's going on. This is super interesting. So the two tensions, there's one where the Hubble constant estimated from cosmic microwave background and from local standards is disagreeing, and now at a level where it seems like it's a real disagreement and not measurement error. And there's another where there's several ways of measuring dark energy density and whether that's varying, and they're suggesting it's varying. And so both of those are suggesting there's something deeper than a cosmological constant going on, but we don't know what it is. And that's just a little bit of a tangent into cosmology, but we went back to, and why did I not slide in order anyway? We went back, as say, we observed another deep field in the south, but those are both pencil beam surveys, and you can't get good statistics with pencil beam survey. And also around about early 2000s, the Spitzer Observatory was launching in the infrared, and its field of view was much wider than Hubble's. And we wanted to do a deep field with Spitzer. So if you do a deep field with Spitzer and you want to get Hubble images of all the same area, you have to do a big deep field with Hubble. And we decided to do two, one in the north and one in the south, and called this the Great Observatory Forest and Steep Survey. So did the wider area, multiple epochs, multiple observatories, multi-wavelength. And since this is going to be a huge project, instead of taking the exposures all at the same time, let's spread them out in time and find those supernovae that are turning out to be so important for cosmology. And so we spread them out and found lots of high redshift supernovae from the same survey over a period of about 3 years. And round about the same time, there was a new camera. We used that for the good survey. New camera installed called the Advanced Camera for Surveys. Factors of several more sensitive than the camera that took the Hubble field and a wider area. And so instead of finding things at redshift of 3, it was now able to find things at a redshift of 6. And that was sort of the limit of the redshift. So now instead of looking back 2 billion years, within 2 billion years of the Big Bang, you're looking back to the 1 billion year of the Big Bang and finding dozens of galaxies. So I think I left out a slide, but I wanted to circle back to the cosmology to say that cosmological change in our thinking essentially solved the same faint blue galaxy problem, because the volume of the universe projected on the sky is different in the different models. So in fact, you expect to see more galaxies projected on the sky. That more or less, you didn't need to do crazy things to galaxy evolution. You had to do crazy things to the expansion of the universe to solve the faint blue galaxy. Come 2010, we did a big survey we called the Cosmic Assembly Near Infrared Deep Extragalactic Survey, or CANDELS, misspelled. But you can still see every December that there are peaks on the searches for CANDELS. So that was about 3 months of Hubble time spread over 3 years. In the optical and the infrared, it used that Advanced Camera for Survey and a Wide Field Camera 3, so the 3rd generation wide field camera in the infrared. We were finding galaxies out to redshifts about 50. Hubble's record by the time James Webb went up was a galaxy that was pretty much everybody believed the spectrum was confirmed at a redshift of about 11. 10-ish or 11. But there was only one of those, and we were finding a handful out of redshift to date. And then we were finding things that we didn't see in the optical at all at lower redshift, and they didn't show up in the optical because they were so dust obscured that they were dropping out of the optical. And those galaxies actually contribute significantly, especially at the bright end, to the star formation rate density. So all sorts of interesting things when you look at the sky in different ways. We also spread those out, and so we found a whole bunch of more supernovae and found them out at higher redshifts than we find them before. Those ones are not quite as essential for cosmology because you're already back when we knew the universe was decelerating, but they're interesting for actually understanding the evolution of chemical elements and galaxy evolution and so on. So we were finding a bunch of those. And we were finding lots more galaxies. And so this is sort of like summarizing where we were roughly a year before Webb launched. We now had enough galaxies at redshifts above 3. As I said, our breakthrough with the Hubble Deep Field was redshift of 3. We're now able to make a histogram that goes up to 1200 of galaxies that we are pretty sure go out to about a redshift of 8. And then we can take that Dow diagram that I showed you from the first Hubble Deep Field, and we can actually plot that with error bars out to redshifts. This was a guess, I would say, out to redshifts about there. It was probably pretty reliable. And James Webb launched. So James Webb, so Hubble's mirror is 2.5 meters in diameter. James Webb has 18 mirrors that combine to give it a 6.5 meter diameter primary. And they had to fold up and unfold. And then the whole thing is cooled. So that launched on Christmas Day in 2021. It is operated from the building that I work in Baltimore, Space Telescope Science Institute. I have never actually physically been in that room, so I do not operate this telescope. I get the data from it and from the archive. But it's very cool that we have the operations center right at that room. So the telescope's orbiting it's orbiting around the second Lagrange point in the Sun, Earth, Moon orbital system, which is a stable orbit where it can orbit the Sun at about the same rate as the Earth orbits the Sun, even though it's orbit further out. And that means you can put a sunshade between it and the Earth and the Sun, and you can shade the telescope. The telescope passively cools to about 30 degrees above absolute zero. And that means you can observe in the infrared without the thermal background of your telescope overwhelming things. So that's the trick for James Webb to be able to observe in the infrared. And that whole mirror, the whole thing had to fold up in a rocket, unfold. This is the sunshade's about the size of a tennis court. And then the mirror had to unfold along these segments, and then everything had to be aligned. I was convinced something disastrous had to go wrong. There's so many moving parts on this, many more than Hubble. So it is amazing that almost everything has worked perfectly, and the few things that haven't worked perfectly are 20% kind of problems. They're not. Many of the instruments actually exceeded their sensitivity expectations. So infrared light, you can see things that we tend to think of as heat, but it's the radiation, thermal radiation from people. So you get a different view. So in some sense, you can see through the plastic bag because you're seeing the heat from that guy's hands. So you get a different view. You can use it. It's used all the time for like security cameras at night because people glow in the dark in the infrared. And so this really is optimized for the infrared. It has a camera on board called the near infrared camera, field of view that's a good bit bigger than like about twice the size of, 3 times the size anyway of Hubble's infrared camera and goes out to much longer wavelengths. And then one that goes to even longer wavelengths, mid-infrared camera. It has a guider and spectrograph, and then near-infrared spectrograph that can take a whole bunch of spectra at once. Big workforces for the kind of work I'm talking about, near-infrared camera spectrograph. So it's up there, first few days of observing. A friend of mine likes to pull things down from the archive and post on Twitter, and this was one of his posts that I really liked. What is that? It's a nearby galaxy. It's that galaxy, so that's the ground-based picture. NGC 723 or something like that.
628.
628. And that's that same picture from the ground. There's Hubble, so you can see higher resolution, but essentially the same wavelengths. And then as we go to the infrared, now this is a composite of several different infrared bands, all of which are longer wavelength. But the thing that's giving you that modeled sort of percolation kind of appearance is the mid-infrared at about probably about 18 microns, maybe a bit shorter than that. But it's picking up dust emission from the interstellar heat. So in those previous images, you're seeing the stars, and you're seeing the dust and absorption. And in this image, you're seeing the dust and emission. And the other thing that I really find delightful about this particular rendering is amateurs grabbed the images from Webb, and you've got a bunch of different filters, none of which are the optical wavelengths that our eyes are sensitive to. So you are free to adjust the color map in a way that you think makes sense. And so this was an amateur adjusting the color map in a way that I think is actually a very good rendering of what's going on there. And okay, so we're actually probably learning things from this. I actually have not seen a definitive paper yet analyzing what's going on with those patches and those holes and things. But if you do supercomputer hydrodynamical models of the interaction between stars and the interstellar medium, the stars, they have clusters, they form in clusters, the clusters have supernovae, they explode, they blow out these bubbles, so on and so forth. So you get a patchy interstellar medium, and depending on what you put in for how the energy is transferred from the small scales to large scales, you're going to get a different, this is all the same initial condition. They're not modeling the stars, they're modeling the gas, and you want to get all of that to look like what nature actually gives us. So now we have the data from James Webb, where you can actually say, okay, which of these models is right? What is the physical prescription for that physics of how you get the energy from small scales to large scales? And I say, I've seen a paper or two on this, but I've not seen anything that actually cracks that and said this is what's going on. This was another very early observation. This one, second one was taken, the one I just showed you was taken, I think, a week after or two after they opened up for general science. This one was taken as early release observations, so was taken really just to show off the telescope, and astronomers were not allowed to do science with it until it was released to the public. But it's a cluster of galaxies. The cluster itself is at about a redshift of 0.3 or 4. And then there are background galaxies that are gravitationally lensed by the cluster, and they are stretched into weird shapes by the gravitational lensing. This is the Hubble image of that cluster. This is a little bit of an unfair comparison because that's not a very long exposure with Hubble, but this wasn't a very long exposure with Webb either. But that's the Webb, so you're just getting more detail because you have higher resolution, and you're getting much more sensitivity, and you're seeing things that are higher redshift because they just aren't there in optical. And you can take that near spectrograph and put an aperture down on individual galaxies, and you can disperse the light, and you can't read it, but this is hydrogen, oxygen, so on. They're actual individual spectral lines that you can tell what chemical elements are in these galaxies. And one of these, I don't remember which one, is at a redshift of 8. And that was an observation that was just taken to show off. Nobody thought you'd be getting a spectrum of a redshift 8 galaxy in the first spectrum you took with the telescope. So it is now a machine for doing this. The one that I've been most involved in the survey with James Webb is called SEERS, Cosmic Evolution Early Release Survey. Was about 65 hours of exposures spread over a year and a half of observing and spread over 11 different fields, all next to each other. We used all the instruments because that was part of why we got the time early, was that we will test out all the modes of observing and have about 100,000 images of galaxies. And then spectra, we had spectra of those, and I'll show you and we're getting more spectra now. Slightly later than that, there's another survey that all the data have been obtained and put together. The deepest image is now 120 hours spread over 2 years, the NGB survey, and that also had some spectra going along, but not at the same field. So that's about a 50th of the area of that CANDELS survey, so narrower field, but much, much deeper. I just want to zoom in because it's gorgeous. And zooming in even more on the part down in the lower left. So there's just huge amounts of information. You're now looking at things here that are about 31st magnitude, but it's an infrared magnitude. So, but you know, a photon per month, strikingly tiny.
What is the lovely magnitude?
That's about
That's not it.
Yeah, this is the deepest image that's been taken. So you could go longer, but that's all you can do. Just observe, take more pictures. Which we have proposed to do several cycles in a row. I haven't got the time to do it yet. But now you want to take that spectrograph and you want to say, can we really see where these galaxies actually are? So in the first week of observations, 2 different teams looking at the SEERS data found 2 galaxies that we were very excited about. We got one that we thought was at a redshift of 14. We named it after the principal investigator's daughter, Maisie. And by the time we published it, we realized there was a data reduction problem, that it was actually about a redshift of 12. Eventually got a spectrum, it's redshift of 11.4, and you can see that line and break just right there. Tells you the redshift right on that. There was another one, a different team thought it was at a redshift of 16. We had it in our catalog and we didn't pay attention to it for one reason or another. And I don't remember the exact reason, but we didn't publish it. And we were a little skeptical of the redshift of 16, but it was the best fit. Seemed implausible, turned out not to be redshift of 16 for reasons that were sort of interesting. There was a very, very bright H alpha line that happened to fall in the right place to just mix up the photometric estimates. And so you really do need to get these spectra to figure out, is that galaxy really a distant galaxy or is it somewhere in between? Still might be an interesting thing if it's in between, but you're just searching the more distant ones. And so now with several years of Webb, now we're looking back to within a few 100 million years of the Big Bang, and we can do that Maddow diagram out to even larger distance. The top of this is the cosmic star formation rate. We can also start to do a cosmic black hole accretion rate, which is the rate at which gas is being absorbed, eaten by black holes. And that turns out to be over most of cosmic time about 1% of the star formation, but not always. And how well did the predictions bear up? So this is just a count of how many galaxies you see out at redshifts, almost up to 14, although the last point on here is 12. And here were models, all of which were published before Webb launched, and most of them are under. So we're seeing more galaxies than expected. Most of the models predicted, and they're brighter than predicted. And something's going on. And we don't know exactly what. Then we're also getting, now there's a ongoing survey to do many hours of spectroscopy to get tens of thousands of spectra. We should have hundreds above redshift of about 10. And already we're finding things like the most distant black hole from the data that's coming in. Going back to some of these deep fields, saying, well, okay, we found galaxies about a redshift of 14. What if we're crazy and we look for even redder things? Are there any there? There are. Could they be at high redshift? Maybe. So there's about 9 good candidates at about redshift greater than 16. And a few of them are at a redshift, preferred redshift of 25, but we don't have spectra. So we don't know. We have a few candidates at a redshift of 30. Probably not. The thing that would masquerade as a galaxy with that red would be a brown dwarf in our galaxy, so a failed star, and it would have a temperature that's about room temperature. So it'd be very cool, like a brown dwarf, and it would have to be about 3,000 light years away to be the right brightness. That star, if we just wait, its motion in the galaxy is probably enough that it will move, and we could verify it just by waiting. We're impatient, so we propose to get spectra, and the spectra would also tell us whether it's a brown one. So we have some time now coming up to test at least a couple of the candidates, see whether they're out there. There are a couple of surprises. I'm getting on. I'm pretty much out of time here. So a couple of surprises from looking at distant universe with Webb. One is I told you that the intergalactic medium eats away all the light. So here's a galaxy at a redshift of 13. Here's the break where it should be, and there's a line that's the hydrogen alpha line, hydrogen Lyman alpha line, and you can see a blow up of it there. It's getting through the intergalactic medium somehow. Probably because this galaxy has blown a bubble. It's ionized a huge bubble in the intergalactic medium, but we did not expect to see that at a redshift of 13. So that's super interesting. And then we're finding all these things we call little red dots. They are little, they're very faint, they're almost unresolved, so they look like stars, and they're very red. The first talk I heard about them was a guy, collaborator in the Sears collaboration, who said, I just went and looked for the reddest things, found 40 of them. They were all essentially unresolved, but they all had spectra that didn't look like any stars spectra. And so so we've got spectra of a bunch of these, and not all of them, but many of them have broad lines of hydrogen or oxygen. And broad line is a classic signature of a disk of rapidly moving gas spiraling into a black hole. So that was the initial thought was, okay, this is an active galaxy, happens to be red, we got to figure out why it's red. When people started scratching their head on how can it be that red, a favored model is you have a very dense cloud of hydrogen, but almost no heavy elements. So there's no dust, just have hydrogen, very dense. That very dense can give you the red colors, great, but it also would broaden the line itself. So now it's not obvious that the line's being broadened by spiraling into the black hole, it may be broadened by the dust, the cloud around the black hole. So there's lots of interest in these little red dots, lots of follow-up to try to figure out what's going on there. And then we're also using these gravitational lenses to magnify the background galaxies, look for even fainter ones. So there's a big project going on now called Venus, vast exploration of nascent unexplored sources, which I think is the worst acronym ever studying distant galaxies, but I was not going to argue about acronyms. And so far we haven't found any record holders in that survey, though that survey is ongoing. But we're also spreading those observations out and many of these clusters of Hubble and finding supernovae that have gone off. And in some of the supernova, we're seeing an image of a supernova, but that supernova, the image of that galaxy with the supernova has been split by the gravitational lens. So in fact, there are 4 images of the supernova, but they don't all arrive at the same time. And so we have one where we see the fact that it's a supernova and we see a light curve of one of the images, and we can predict that the next image will appear in 60 years. To wait a while for that one, but there's another one that's going to appear in 1 or 2 years. There was one of these found with Hubble, and the prediction was bang on. People, teams went back and observed it, and in fact, the next image did appear. So this is a big tool now for understanding cosmology, because you can do cosmological estimates at that time delay. So just a real quick summary. So we found lots more galaxies at redshift of 9 than expected. Only a handful of the ones we've seen seem to be primordial in chemical abundances, which is a little bit of a head scratcher. You would have thought you're seeing the first galaxies. We're not seeing the first galaxies. Star formation was probably different, probably more efficient at forming high mass stars. The early galaxies have central black holes, but we didn't expect them to look like little red dots. And we really don't understand the growth of the black holes and that interplay with stuff. There's lots still to uncover in the early universe. I am not going to spend any time on Nancy Grace Roman, except to tell you there's another telescope that's going up. It's going up in August now. We've actually moved up. The launch date that Congress holds us to is March of 2027. And we're planning to get it off in August of 2026. It has a primary mirror about the size of Hubble, but it can observe the sky 1,000 times faster. It is a near-infrared telescope primarily, so it goes from the red part of the optical spectrum to the near-infrared part of the spectrum.
What's the coding thing?
The coding for the mirror, I'm not actually sure, probably magnesium fluoride, but I'm not absolutely sure.
What was that?
Maybe magnesium fluoride over aluminum or something, or not, or I don't know what actually is it's coding at the time. Not gold. Yeah, so this is the footprint of the camera, and this is the footprint of Hubble's camera. So that CANDELS survey, which was 3 months of Hubble, we could do in a day and a half. So it's made for big surveys. I'm out of time. Most of those surveys are cosmologically oriented, so not quite so much early universe, but trying to figure out what's going on with the expansion of the universe and also the identified exoplanets.
All right,
Yeah.
question to it.
Yeah.
Yeah, you got a wider field. What's
Yeah.
the resolution?
So it's about the same as Hubble. So the
Really?
pixel size is about 1/10 of an arc second. And that is undersampling the point spread function. So it has the same size mirror as Hubble, same resolution, but it's a little bit more undersampled than Hubble's. Let me just flip through. Yeah, I think that's where I will leave it. I have some pretty pictures of it. Want to leave time for any further discussion. That.
Wow.
Yeah.
Well, thank you. I get the first question.
Yeah.
What's not to understand about the growth of black holes? You get near it, you get spaghettified, it eats you. Everybody knows you eat spaghetti, you grow.
Yeah, exactly. So I would say one of the big questions, and some people think this is a huge problem and other people don't think it's so. But we know that there are galaxies at a redshift of 6 billion years after the Big Bang that have 1 billion solar mass black hole. And when you are eating that spaghettified gas, if you eat it at a certain rate, you eventually hit what's called the Eddington limit, where the radiation pressure of that radiation of the outgoing gas is balancing the gravitational pressure inward, and that is thought to stall the accretion of gas at a certain rate. And therefore, you can't grow fast enough to get from a stellar mass, which is thought to be where you start, to a billion solar masses in a billion years, unless you violate that Eddington limit. And there are all sorts of ways you can think of that nature might violate that limit, but they're very, very hard to test whether they actually happen. So for some people, that Eddington limit is like, that is a real, showstopper, and for other people, it's like, okay, we can make the geometry different, we can have it, like, there are all sorts of different ways you can, yeah. So that's, but now we're out at where we can do, instead of having that redshift 6 be where we know the black hole mass is, we're starting to get pretty, I wouldn't say really good estimates, but estimates anyway, of black hole masses at redshift of 9. So we're going further back in time where we now have black hole mass estimates. We can push further back to see is that still a problem.
Great, thank you.
Yeah.
Questions in the room?
What about the galaxy morphologies at those higher redshifts? I know that from the Hubble data, that they were talking about galaxies that look like pickles.
Yep. Go back to one of the early slides to show you a pickle galaxy. Way back. Yeah, that one, man.
Whether it was dill or
Yeah.
spicy.
So a lot of them, when they're close enough or big enough, so this was redshift about 3. Yeah, a lot of them have these morphologies, and okay, so it's early in the universe, things are forming fast, so they don't have time to settle into a nice organized disk. So that's one way to think about it. And that may be part of the explanation. I think it would be super interesting to take a whole bunch of these galaxies, and now that we have Webb, let's measure the velocities along that. Because if that's a pickle that's a flat thing seen edge on, this side's going to be coming toward us, and that side's going to be going away from us. If that's 2 things falling toward each other, they're going to have the same velocity. So a lot you can tell, especially if you got even a dozen of these in a statistical sample. Haven't done yet.
None of those acronyms are focusing on that.
Well, so at those higher redshifts, they're all so small that we don't have the richness of morphology that we have at a redshift of 3 to get excited about. So most of them look like sort of diffuse blobs. But when you have one bright enough, they do look disorganized in one way or another. And a bunch of them are pickle-like. We've done some statistics, not at the super high redshifts, but at these, even out of redshift of 5 or 6 now. Just simple statistics on what is the distribution of the ratio of the major to the minor axis. Because if you're just looking at disks from a whole bunch of random angles, that is going to be different from if you're looking at cigars at a whole bunch of angles. And it looks more like cigars. But that's the extent to which we've really constrained it. Yeah.
Seems to me you could go back a couple more red shifts and find the cucumber galaxy.
Yeah, exactly. Yeah,
That would answer your question.
for sure.
Anything else in the room?
It's one possibility, this is stuff about the galaxy, but every once in a while, there's some ringer that you find some very interesting factor on that nearby exit. You know, you can sort of have this analyzing.
The exoplanets are amazing, and like every day there's something fascinating.
But particularly,
yeah.
like, organic compounds.
Yeah.
So these things, but, is that really neat? I don't know.
Yeah, I
It's very
think
exciting times.
it's super exciting. I think right now so the one that was, I would say, exciting and controversial 6 months ago, maybe a year ago, was a claim for finding chemical signatures that were indicative of life because they were out of equilibrium, and therefore you really need to, it's hard to explain them with chemistry of an atmosphere that's in. And the controversy was that argument wasn't ironclad, and the the actual detection of those lines depended on a model that you had to fit to subtract out some confusions. So I would say half the people who I talked to thought that that was not a secure conclusion from that particular measurement. So we certainly found planets with water. We found planets with, oxygen, there's the stuff of chemistry of Earth, but the smoking gun for like feedback from life would be out of equilibrium chemistry. That's much more subtle and nobody's really conclusively.
You might not have enough signal.
It's on the edge, yeah. It's really on the edge. And you need the favorable, like really favorable star brightness, planetary distance, so on. A lot of these are so close to the star that they probably are not in the same conditions of temperature or orbital properties that the Earth is. So even if they have organic material, it's not probably like Earth.
Any questions online? Alan?
Not for me tonight. Great presentation, though. Thank you.
I got a question.
I have a question.
Sure.
Arthur, Kurt?
Hi. The Hubble telescope's been really such a success. How much longer do they have with that telescope? How much longer is it going to operate, and what condition is it in?
Yeah, so it's in, it hasn't been touched since 2009. And all of the equipment is past its guarantees, right? It's not under warranty anymore.
Shucks.
So we're living on borrowed time. The orbit is not decaying as fast as expected, so we're good at least through the mid-2030s as far as the orbit goes.
How are the gyros?
Was that gyros are okay. Gyros are also like, I think we could go down to 3 and be okay. We have fine guidance sensors with some redundancy. We have reaction wheels with less redundancy. I think those are pretty hardy. The instruments themselves have been slowly degrading. So everything's a little more painful and messy. There's lots of hot pixels in the detectors. And so it's less efficient, but on the other hand, it's less in demand. So now you can get a lot more time to do things that just take longer because the instrument's not as sensitive as it was. So it's still a factor of roughly 10 oversubscribed. People are coming up with ideas and things to do with it that either you hadn't thought of, you couldn't do before.
That's good to hear.
Yeah. So I think I'm a little worried that the batteries give out maybe as the first thing, but I don't know anything in detail about that.
Mike, I do,
All right, Vivek,
I do
you're
have a
next.
question.
Alan,
I have
Vivek with Kurt.
Hi, yeah, thanks. The question I had was in one of the images that you showed from the web of the galaxy, it had these intricate structures in it. What are those? What do those represent?
That one.
So like filaments.
Yeah, like that one here.
Yeah.
Yeah.
What are those structures?
So what we think is going on is that what you're seeing here is the interstellar gas, and there are pockets of star formation, and the pockets of star formation will clear out by feedback, either from winds from the stars or from a supernova exploding. They'll clear out their local environment. So what we're seeing is that effect of that clearing out that's pushing the gas into these sort of spherical structures, and then probably new stars will form where the denser gas is collecting on the borders of those structures. So you have a feedback cycle that gives you this sort of percolation pattern.
And so this is an infrared image?
This is an infrared image, exactly, yeah.
Thank you.
All right, Alan,
Yes, it's a silly question, but I have forgotten what happens to Hubble in the 2030s. It's a pretty big item to just burn up in the atmosphere, isn't it, or is it not?
Yeah, so by treaty, they can't let it re-enter because it has a greater than 1 in 10,000 chance of falling on someone. So the plan is they will deorbit it. So there is apparently a design of a booster to go up and attach to the back of it. And you could deorbit it, or you could raise it high enough that it'll never come back. But they have to do something, and I would say they don't know yet which of them to do.
And what is deorbiting?
Deorbiting means you just do a controlled reentry so it falls in the ocean.
Oh, okay.
On city.
Thanks.
It's a great picture.
Isn't that? Yeah.
It's fascinating. It looks like Mandelbrot sets should be in there somewhere.
Looks like a hurricane.
Yeah, yeah. Yeah, just
Let me sneak one in here
Yeah.
before I forget it. How much of that is gravitational and how much of that is magnetic?
I would say most of it's not magnetic. Magnetic fields are measured for interstellar media of galaxies, but they're not like dominating the forces.
Okay.
So it's a mix of gravity, which is keeping the gas in there, and the feedback, which is trying to push it out.
Thank you.
how much is dark matter of this image?
In the central regions of galaxies, the dominant gravity is coming from the stars we see. There is dark matter, but it's less than half of the total gravitational attraction. When you move out sort of to the edges, probably even beyond this edge of this image, there are not so many stars, but there's still lots of dark matter. And the dark matter starts to completely dominate when you get out. If you get out to maybe 3 or 4 times the radius of this image, it will be dark matter dominated. And you can measure, there's still gas, you won't see the stars. There's hydrogen gas out there, and you can measure the velocity of the hydrogen gas. You can see that if there weren't dark matter, it wouldn't be rotating around this central thing because there would be nothing to pull it back in. So there has to be this dark matter pulling.
That hauntingly blue center, is that significant?
Well, the stars there have probably, well, A, there's not much gas there. B, there's a bunch of stars there. I don't remember in the center of this galaxy whether there's a star forming cluster in the middle that could have been blowing that out. Or whether,
Mario?
yeah. It's also that the gas gets heated up because everything's moving faster in the center. So I'm not sure which.
All right. Any more questions online? This is our chance. Thank you.
Thank you.
Thank you.
Whole lecture, awesome.
Thank you.
Very much. That was wonderful.
Yeah,
Very
thank you. I
appreciated.
really enjoyed this.
Have a great weekend.
Learned a
All
lot.
right, everybody, I'm gonna close the doors. Wait, don't go. In the
Okay.
room, sit down. Please sit down.
It's just us he's throwing out.
Why is he making everybody sit down?
Stephen Elaine, would you stand up for a second?
Oh.
That's Steve over there eating a cookie. And that's his lovely wife Elaine. Where are you guys gonna be at the next GAAC meeting? They're moving to Socorro, New Mexico.
Oh,
I'm not
congratulations.
telling you that because we're going to miss them. But we are. Here's the deal. Here's the deal. This is important. One small thing. Steve and Elaine have been half of the crew that has stayed an extra 20 minutes or half an hour at the end of every single GAAC meeting for the last 20 years, helping us sweep the floor and clean up and wash the coffee pot and things. And so the next GAAC meeting, they won't be there to help with that. We can handle that with the 2 or 3 people that we've still got on the team, but we need some volunteers. Now, if you volunteer, we're going to count on you, so don't volunteer lightly. All right, but you can reach me by going to our website, clicking on contact us, and us is me. All right, if you want to volunteer, drop me a line from the website so that I can know when to stop begging. Okay, that's all I had to say. Thank you for all your help, Steve and Elaine. All these years.
Thanks, Stephen, Elaine. Happy
Good
night.
trails.
Best of
See you
luck.
online.
Good night.
Good luck
Good
in your
night.
See
new
you online.
Good night, Patty. Dennis.
Right.
Au revoir. Arrivederci. Adios.
Believe me.